Hey everybody, welcome back. In today's video, we are going to learn about section 7.2 of our elementary statistics textbook. Make sure you've already watched my other video on section 7.1. So in 7.1, we were estimating a population proportion. Remember, a population proportion is represented by the letter P. We covered a lot of techniques in that section in 7.1 that we're going to be also using today in 7.2. But in 7.2, instead of estimating a proportion P, we're going to be estimating a population mean. And remember that the population mean is represented by the Greek letter mu, which we've seen quite a few times in this course. And don't get mu confused with the sample mean. So the sample mean is actually x bar. X bar is going to be our point estimate that we're going to be using to construct a confidence interval, just like we did in 7.1. But now our confidence interval is going to be for mu instead of for p. Okay. So what are we going to be learning about? We're going to, as I just said, we're going to use the sample mean x bar as our point estimate, just the same way we used p hat, which was the sample proportion in our last video from 7.1. So in our last video, we used p hat as the best point estimate for p. Today, because we're estimating the population mu, we're using the sample mean x bar as our point estimate for mu. Okay, but our goal here is still going to be to construct a confidence interval. So remember, your point estimate, which is x bar, is just a rough guess, and then the confidence interval will be a more educated guess, where obviously we have to do more math. Okay, so the point estimate for mu, the best point estimate is the sample mean, which is x bar. Okay, and then confidence interval, we're going to construct a confidence interval for mu now using the sample data, and you're going to notice that it's very similar to the formula we used in the previous section. So in 7.1, in the middle of our confidence interval, we had p. Now in the middle of our confidence interval, we're going to have mu, but it's still going to have the same format. Okay, so it's still going to be quite similar to the confidence intervals we constructed in the last section. It's just because we are estimating mu, we're going to have to learn about a new distribution called the student t distribution. So on all of your homework questions and your quiz questions from this section, and then also on the exam, we are going to go under the assumption that when we're constructing a confidence interval for estimating the population mean mu, we're going to go under the assumption that sigma, which is the standard deviation, is not known. And the reason we're focusing on that for our homework quizzes and exam is in the real world, if you ever have to do statistics in the real world, like a study, in most cases, sigma is not known. It's a very rare case where sigma is known. So we're focusing on the most practical type of confidence interval. So we're trying to estimate a population mean when we just have this little sample. So how do we do it? Just to review the notation, what we're trying to estimate is mu, which is the population mean, which we can't really know the true value of unless we do a census. And in most cases, we can't do a census, so we have to make a confidence interval instead. Okay, x bar is the sample mean. That's our best point estimate. S is the sample standard deviation. We're going to have to use S because we're working with the assumption that we don't know sigma. Sigma is not known. And remember, sigma actually represents the standard deviation for the whole population. And if you think about that for a second, it should make sense that we wouldn't know sigma, because we don't know mu because we can't do a census in most cases. So we also wouldn't know sigma, the population standard deviation. So what we do have is S, which is our sample standard deviation. And then we have N, that's the number of sample values. This is the same letter we've used throughout the semester for our sample size, or the number of data values. And then E is the margin of error. Now the formula for E is going to be different than the one that we used in the last section, okay? But the reason for that is we're not estimating P, we're actually estimating mu today. So that's why it has a different formula for the margin of error. Okay, now the requirements that we need to construct a confidence interval is, as always, we need our sample to be a simple random sample. And then also, either or both of these conditions are satisfied. Either the population is normally distributed, or n is greater than 30. So remember, in section 6.4, we learned about the central limit theorem, which basically said that we can use the central limit theorem as long as the population is either normally distributed or n is greater than 30. So that's where this condition came from. So when you use the central limit theorem, that allows us to work with x bar, and that's what we're going to be using as our point estimate for mu. Okay, so let's get into the formulas here. So the formulas we're going to be using in this section, like I said, for the confidence interval, this formula looks kind of similar to what we did in the last section. So just for reference, I'll write the formula we used for our confidence interval in 7.1, which is my last video that I released. So in 7.1, remember we were estimating P, and our confidence interval looked a lot like this. It's just instead of x bar as our point estimate, we had p hat. So it was p hat minus e. Okay, so p hat minus e was less than, instead of mu, we were estimating p, so p went in the middle. And then on the right side, we had p hat plus e. Okay, but if you look at this, this formula right here is what we're doing today that's on the slides. That's 7.2. So notice that they're very similar for the setup of that confidence interval. In fact, it's really just the same setup. It's just because today we're going to be estimating mu. Mu goes in the middle instead of p. And the best point estimate for mu is x bar. So x bar is replacing p hat, which was the best point estimate for p in 7.1. Okay? All right. So with this information, remember there are other ways of writing your confidence interval. Not too incredibly important, but you can also write your confidence interval as x bar plus minus e, as we saw in 7.1 with p hat plus minus e. Or you can write it with an interval notation, so parentheses x bar minus e, comma, x bar plus e, parentheses. Okay, now what's new today, the other thing that's new, other than the confidence interval, is the margin of error. So because sigma is not known, we can't use the standard normal distribution for our critical value. So in 7.1, we actually used the standard normal distribution, and we had our critical value was given to us on the bottom right corner of table A2. Well, today, our margin of error is going to be a little bit different. So it's a new formula. It does have some similarities to the other formula, but the big thing that's new here is our margin of error E equals T sub alpha over 2. So it's T instead of Z. And we're going to have to calculate that critical value, T sub alpha over 2, using what's called the degrees of freedom. So the degrees of freedom is abbreviated as df equals n minus 1. Okay? And then the rest of this will be given to us in the problem, the rest of this formula. So remember, you can always calculate the sample standard deviation S on a calculator or by hand. We did it earlier in the course. But fortunately, in your homework quizzes and exam, they've already calculated S. So S is just going to be the sample standard deviation. And then in this denominator here, the square root of n is the number of data values. So that should be pretty easy to find. Okay, so let's go on to the next slide while I erase this. So our goal is to construct a confidence interval for mu, and the confidence interval is associated with the confidence level, as we saw in my last video, such as the most common one, of course, is 0.95. And remember that alpha is the complement of the confidence level, which means even though we don't need alpha a whole lot here, in 7.1 at least we didn't need much. Here we're going to need it in order to use table A3, which is actually the new table that we're going to be working with today. Okay, so if you have a confidence level of 0.95, how do you get alpha? Well, the formula is just alpha. Looks like a little fish or sort of like a lowercase a, but it's the Greek letter alpha. Alpha equals 1 minus our confidence level. Okay? 1 minus our confidence level. So, for example, if our confidence level is 0.95, how do they get alpha equals 0.05? Well, they just do, using this formula, our confidence level is 0.95. So alpha is going to be 1 minus 0.95. So on a calculator or in your head, if you can do it, that means alpha is 0.05. Now, why do we care about alpha? Well, like I said, we need it in order to look up the critical value T sub alpha over 2. Okay, so T sub alpha over 2 is the critical T value, and whenever sigma is not known, which is the way it is in most cases in the real world, you don't know sigma because you can't do a census. T sub alpha over 2 is the critical value separating an area of alpha over 2 in the right tail of the student T distribution. Okay, so if the area in the right tail is alpha over 2, that means the area in the left tail is also alpha over 2, which means that the area in two tails is going to be alpha over 2 plus alpha over 2. And then alpha over 2 plus alpha over 2 is alpha. So this alpha that we're just talking about here, you can get it from 1 minus the confidence level, and it's actually going to represent the area in two tails. And even if you don't entirely understand what that means yet, just remember that alpha represents the area in two tails. I mean, if we look at the graph, The graph of the student t-distribution is still bell-shaped and symmetric. It's not exactly the same shape as the normal distribution, but it's close to it. Well, if the area on your right tail is alpha over 2 and the area on your left tail is alpha over 2, that means the area in two tails, in other words, the left side plus the right side, has to be alpha. Okay? So just remember, alpha is the area in two tails. We're going to need to use the area in two tails when we actually calculate the critical value. Okay, and then the other new thing here that I already mentioned is the degrees of freedom. So the degrees of freedom is abbreviated as DF, and it just equals n minus 1. It's the number of degrees of freedom used when finding the critical value. So that's the other thing that we're going to need when we're actually using table A3. The round-off rule just says that when you're using an original set of data values, round the confidence interval limits to one more decimal place than is used for the original set of data. If you're using summary statistics, we're not going to be using this. So we're just going to be focusing on, well, if they give us the summary statistics, then we can round to the same number of decimal places. But if we're working with the original set of data values, then you want to include one more decimal place. But honestly, on your homework quizzes and exams, they will tell you directly below where you type in your answer, they will tell you what to round to. So they'll say like round to 3 decimal places or round to 2 decimal places. So this isn't really going to be that helpful because it'll be pretty obvious based on what they tell you. Okay, so this student t-distribution is what we have to use because we don't know sigma. It was invented a long time ago to deal with small sample sizes where we don't know sigma for the whole population. So if a population has a normal distribution, or if n is greater than 30 for the population, then the distribution of t equals x bar minus mu over s over the square root of n. Notice this looks very similar to the formula we used when we were doing the central limit theorem, which should make sense why it kind of has to follow the central limit theorem. This is a student t-distribution. Student doesn't have anything to do with anything. It's just a name. Okay, it doesn't mean that you're a student for using it. Lots of professionals use this distribution all the time. It's for teachers, it's for students, it's for scientists. Anyway, student t-distribution is for all samples of size n. Okay? And the nice thing about it is if you know it's from a normal distribution, your sample size n could actually be quite small, like you might only have 6 data values, but you can still use this, okay, which is what makes it such a useful distribution. A student t-distribution is commonly referred to as a t-distribution. Okay, so I'm just going to call it a t-distribution. Degrees of freedom, like we said, that's n minus 1. And in general, the number of degrees of freedom for a collection of sample data values is the number of sample values that can vary after certain restrictions have been imposed on all data values. All right, so for us in our class, all you really need to remember is that the degrees of freedom is the sample size n minus 1. Okay, so that's not too bad. So df equals n minus 1. Okay, so how do you find a critical t-value? You can use technology if you have it. Otherwise, for my video, I'm going to teach you how to use table A3, which is in this week's module. Table A3 can only be used for certain values of df, which is the degrees of freedom, and it only works if your area in two tails for alpha actually shows up as one of the columns. But fortunately, the problems in your homework, quizzes, and exam can all be done using table A3. So if you don't want to use technology, you don't need to. You can just use table A3 and still get 100% if you do everything correctly. Okay? So, the thing is, if your degrees of freedom isn't in table A3, you can still just use the closest value and then work with that. Okay, so the reason we can use table A3 for the student t distribution is, like I said, it's shaped very similarly to the normal distribution. So here in green, we have the standard normal distribution. The student t distribution when n equals 12 is this red graph, which almost looks the same. It's just a little slightly different shaped bell curve. And then the student t distribution when n equals 3 is this blue one here. And that's also a bell curve. But notice that the shape or the distribution of the student t distribution is different for different sample sizes. So basically, the whole reason why we have to worry about the number of degrees of freedom, df, is just because the degrees of freedom sort of control which shape it has. Okay, so because if your sample size n changes, your degrees of freedom n minus 1 also changes, and so you get a slightly different shaped graph. So the student t distribution changes shape based on your sample size, which is why it's so effective. Okay? All right. So the student t distribution has the same general symmetric bell shape. Has the same general symmetric bell shape as the standard normal distribution, but it has more variability, as we expect with small samples. The student t distribution has a mean of t equals 0. All right, so in the middle of the graph, just as we saw with the standard normal distribution, z equaled 0 in the middle of the graph, but here our variable is t instead of z. Okay, the standard deviation of the student t distribution varies also with the sample size, but it is greater than 1. So remember, in the standard normal distribution, sigma equals 1. But for the student t distribution, the standard deviation changes based on your number of degrees of freedom, which is n minus 1. As the sample size n gets larger, the student t distribution gets closer and closer to the standard normal distribution, which we could clearly see in the graphs that we were just looking at on the last slide. I mean, they're all bell-shaped and they're all symmetric, and basically those graphs are actually going to get closer and closer to a normal distribution, but they sort of adapt based on your number of degrees of freedom. Okay? So even if that was a lot and you didn't understand all of that, these problems aren't actually too bad. Okay, so as long as the two requirements are satisfied, the sample is a simple random sample, which all of your homework, quizzes, and exam problems will be, and the population is normally distributed or n is greater than 30, this will automatically be the case in your homework, quizzes, and exams. So with sigma unknown, as is usually the case in the real world, you just use n minus 1 for your degrees of freedom, and then use the t distribution table, which is table A3, to find the critical value t sub alpha over 2. Once we have t sub alpha over 2, then we're going to evaluate the margin of error using this formula, and then we'll construct our confidence interval. very similar process to what we did in our last video in 7.1. Okay, so let's focus on the critical t-value. We keep talking about it, but we haven't seen table A3 yet. So let's start by finding the critical value t sub alpha over 2. Don't worry too much about the alpha over 2. That notation just means that the area in the right tail is alpha over 2. But like I said, it's easier to think of the area in two tails as alpha. Okay, so if we want to find the critical value t sub alpha over 2 corresponding to a 95% confidence level, given that the sample has size n equals 6, we already said that the area in two tails is alpha equals 1 minus 0.95, which is 0.05. So alpha equals 0.05 is the area in two tails. And then our degrees of freedom, df, equals n minus 1. So that means since n is 6, df is going to be 6 minus 1, which is 5. Okay? So let's go ahead and close the slides for just a second so we can look at this table. And then we'll return to this slide in just a second. So here is table A3. I'm going to turn off the camera so I can actually read this thing. So if you look at table A3, it's for the t distribution, critical t values. You're going to need to download it. It's in this week's module. You've got the area in one tail and the area in two tails. And then like we said, alpha is just going to be represented by the area in two tails because the area in one tail is alpha over 2. So just focus on the area in two tails. We're not really going to have to use the area in one tail. And then on the left side, you're going to see degrees of freedom. So in this problem, we said that the degrees of freedom was 5, and we said that the area in two tails was 0.05. So if I turn the camera back on, we said alpha was 0.05. Alpha was 0.05 and the degrees of freedom was 5. So it's kind of obscuring the table, so let me erase that. So alpha is the same as the area in two tails. So if you look at the top where it says area in two tails, here's 0.05. So we're looking at this middle column here. This is the area in two tails of 0.05, that's our alpha. And then we said our degrees of freedom was 6 minus 1, which is 5, which is actually right here. So where this row meets this column, that's going to give us our critical t value, which here is 2.571. 2.571. And remember your critical value or your critical t value. Let me write it up high so we can actually read what I'm writing. Your critical value or critical t value is something we always have to calculate in these problems. It's the same as t sub alpha over 2, and that's this 2.571 that we just looked up. Okay? And just like with table A2, which is the other table that we used, the standard normal table, you need to remember that if you're using technology, you might get a slightly more accurate answer, but it's okay to be a little bit off because on our homework quizzes and exams, they have a built-in compensator for very small errors that are caused by using the table. Okay, so if you want to be more accurate, you can use a computer or technology, but like I said, I like to show people how to do it without using anything besides a table. I know it's a little bit old-fashioned, but that's just, I like to teach that way. Okay. But you're certainly welcome to use technology. I just feel like technology often takes the fun out of things. So anyway, our critical t-value was 2.571. Okay, and if you look on this slide, we can see that they're doing the same process we did, but nice thing here is they actually have sketched the graph. This is the graph of the student t distribution, which looks a lot like the normal distribution. It's just a little bit more pronounced because n is small. So the smaller n gets, the more steep it gets in the middle and the more flat it gets towards the edges. But it still looks like a bell curve. Anyway, we looked it up, and as they are saying here, since alpha was 0.05, that means alpha over 2 is 0.025. So the area in the right tail is 0.025, and the area in the left tail is 0.025. But like I said, alpha is the area in two tails, and 0.025 plus 0.025 is 0.05. So it's easier to just remember that alpha is the area in two tails when you're using the table. Okay? Okay, so if there's 0.025 in each tail, there's a total area of 0.05. Okay, so using technology, they happen to get the exact same critical value we have here, but sometimes, like I said, the technology might be a little bit different. In some cases, it might be a little bit more accurate than the table. But in this case, we actually got the same exact number using table A3 that they got in our book using technology. Okay, using table A3, got the same number. We already went over this. Just remember, it's usually easier to just use the area in two tails like we did. If you wanted to use the area in one tail, then that would be half of 0.05, which is 0.025. But that should make sense, right? 0.025 plus 0.025 is 0.05. That's the area in two tails. Okay, cool. So we've calculated a critical t-value. So really all you need is to just do this process that we did on each homework problem. So alpha is 1 minus your confidence level, and then look up alpha is the same as the area in two tails, and just remember df, the degrees of freedom, is n minus 1. Okay, so let's jump into an actual confidence interval problem. Okay, so I love Reese's Peanut Butter Cups, so I really am glad we chose this example today, although it is making my stomach growl. So listed below are weights in grams of randomly selected Reese's Peanut Butter Cups miniatures. They are from a package of 38 cups, and the package label states that the total weight is 12 ounces or 340.2 grams. So far, they really haven't told us a whole lot that's going to be helpful here. If the 38 cups have a total weight of 340.2 grams, then the cups should have a mean weight of 340.2 grams divided by 38, which is the total number of cups, which is 8.953 grams. And then for convenience, they actually included the weight of, here they've only selected 1, 2, 3, 4, 5, 6 of the cups. Okay? So because there are 1, 2, 3, 4, 5, 6 data values in our little sample, that means right off the bat we know n is 6. So n equals 6. Okay. Anyway, in part A, they want us to use the listed sample data to find the point estimate of the mean weight of a Reese's peanut butter cup miniatures. Okay, and then we'll come back to part B later. So let's look at part A first. So in part A, the point estimate of the data is the sample mean x bar, which they don't have worked out here. But x bar, remember, is where you add up all the data values in your sample. So that's your sample mean. You add them all up and you divide by the number of data values n. So here, what they did to calculate the point estimate is the best point estimate of mu, as we said earlier today, is x bar. So the point estimate is x bar, and remember that the formula for x bar is the sum of x over n. So in this problem, n is clearly 6 because there are 6 data values listed here. Okay, so our denominator here is going to be 6. And then in our numerator, the sum of x means we add all of these numbers up. So I don't want to write that because I don't have enough room to write all that. But it's going to be the first data value, so 8.639, plus the second data value all the way up to the last data value, which is 9.042. Okay, so clearly you would want to do this on a calculator when you have a bunch of decimals like this. So let me get my calculator, and then we will do this. Okay, so we're going to add up the numbers first. So 8.639 plus 8.689 plus 8.548 plus 8.980 plus 8.936 plus 9.042. So I got 52.834 after I added up all the numbers in the numerator. And then we have to divide by n, which here is 6, because we have a total of 6 data values. So if I divide by 6, that's going to give me the same number they got for x bar. So they got x bar is 8.8056, and then the 6 is just repeat. Okay, so let's go back to that slide. They rounded, so even though the 6's repeat, they rounded up, so they rounded it to 8.8057. Okay, so we've got our x bar. Now, the requirement check is kind of optional because, like I said, in your homework, quizzes, and exams, the requirements are already satisfied on all the problems because otherwise we wouldn't even be able to do the math if you think about it. So, but just so you know, the reason this problem satisfies the requirements is even though they didn't say it in the instructions, now they're saying that the sample is a simple random sample. Okay, so that requirement checks out. And then the other requirement is because the sample size is n equals 6, the requirement that the population is normally distributed or the sample size is greater than 30 can be satisfied only if the sample data appear to be from a normally distributed population, so we need to investigate normality. So this is the kind of stuff that you would have to do if you were doing statistics in the real world. But we're doing elementary statistics here, so like I said, we're not going to have to actually determine whether the distribution is approximately normal. But just in case you're curious on how you would do this in the real world, it's on the next slide. So on this slide, they've graphed all the data values. So on the bottom here, they have the weight of each Reese's Peanut Butter Cup in grams. And then on the vertical axis, they have the z-score. And they're saying because the data points appear to pretty closely fit this straight line pattern, they're saying that that means that the sample data appear to be normally distributed. But like I said, we're not going to have to do any of this. So I'm going to go ahead and not spend too much time on this because this is already done on all your homework, quizzes, and exam problems. Okay, but that's interesting to know, just in case you were wondering how they are trying to make the argument that the data is from a normal distribution. Okay, so we already calculated t sub alpha over 2, which they've written as t sub 0.025 here. So we said that was 2.571. We said that the degrees of freedom was n minus 1 equals 5. Now, to find the standard deviation S, we have done that earlier in the course. But that will be, the standard deviation for the sample is going to be given to you in each problem on the homework, quizzes, and exam. So we're not going to have to calculate that by hand. So here they've calculated it for us, and they say that S equals 0.2054. Okay. So now we need to find this margin of error. So the formula is, for the margin of error, it's E equals T sub alpha over 2, which is what we just spent a lot of time going over how to find in table A3, times S, which is this 0.2054. That will be given to us. That's the sample standard deviation, divided by the square root of n. Remember here that n was 6. That's how we got n minus 1 is 5. N was 6, obviously, because there were a total of 6 data values in our sample. So plugging everything in here, we've got 2.571 is t sub alpha over 2 times S, which is 0.2054, over the square root of n, so the square root of 6. So now this is pretty straightforward to type into your calculator. Basically, for example, on my calculator, I would just do, I would almost just type it in directly. So it would be 2.571, and then I would press, so 2.571, and then I would press the times button. And then I would type in the numerator, which is 0.2054. So times 0.2054. And then I would just divide, so I press the division button, by the denominator, which has a square root. So I divide by, I would press the square root button. So on my calculator, square root button looks like a check mark, so just the square root symbol, but your calculator might be different. So anyway, as long as you're comfortable with your calculator, it's pretty easy to plug that in. And then I typed in 6, and then I pressed enter. But this may or may not be helpful because there's so many different types of calculators out there. But you're probably going to type in something like this. And as long as you can reliably get the correct answer during whatever approach it takes with your individual calculator, it doesn't really matter. All that matters is that you can do the math one way or the other. So what we got here is 2.15589, so I'm going to go ahead and round that. So I wrote out a total of 5 digits, just so that we have lots of digits to work with. Okay? And it looks like they actually wrote out 6 digits, which is fine as well. Okay, so we got that same number that they did using a calculator. So that is our margin of error, E, that we just calculated. All right, and then how do we use the margin of error, E? Well, we want to plug it into the formula for the confidence interval. So we're really on step 4 now of their rather long explanation of how to calculate a confidence interval. So in step 4, we've got x bar minus e is less than mu is less than x bar plus e. So basically, since we've already calculated x bar, that was our sample mean, and we've already calculated e, that's our margin of error, we can literally just plug it in to this formula the same way we did in the last section, 7.1. Okay, so we write down this formula, x bar minus e is less than mu is less than x bar plus e. Okay, so this is for a confidence interval for mu, and this is where sigma is unknown. So the formula is x bar minus e is less than mu, which is what we're estimating, which is less than x bar plus e. Okay, and we said that x bar was 8.8057. Okay, so plugging that in for x bar, we have 8.8057 for this x bar here. Ooh, dropped my calculator. It's okay, I have another one if I broke it, but you know, honestly, these calculators are pretty sturdy, so I think it'll be okay. Oh, gravity, always bringing us down. Okay, so we plugged in x bar for here and here, and then we need to plug in e. So returning to the slides, we said e was this down here, so 0.21559 or 0.215589 if you want to write one more digit. So we're going to have minus 0.21559 minus 0.21559. And the reason we're writing so many digits is you don't want to round until the last step. Just to avoid rounding error, you don't want to round each of these individual numbers. You only want to round once you get down to a single number. It's the same process that we did in the last video. Okay, so then if we plug in this left side into our calculator, we got, typing it in, we've got 8.8057 minus 0.21559. That gives us 8.59011. 8.59011. This is less than mu. Remember, we don't know what mu is. This is what we're trying to make a guess about. So mu, we don't know because we can't do a census for the entire population. And then over on the right side, I don't know why I wrote a minus here. I guess I need more coffee, but this is supposed to be a plus. You've probably been staring at that for a while. Sorry about that. I'm not going to redo the video though, so we'll just keep that in there for comic relief. So remember, on the left side we're subtracting, on the right side it's x bar plus e, so this is supposed to be a plus. Anyway, typing into our calculator, we've got 8.8057, which was our x bar, plus e. So here we're going to be doing plus the 0.21559. And that gives us the right side of our confidence interval, so 9.02129. Okay, so this right here is a confidence interval, and then the only thing we have to do is, now that we have it down to a single number on the left side and a single number on the right side, we just need to round. Okay, so let's return to the slides and see what they did to round this. So it looks like they rounded if you look down here at the bottom, it looks like they rounded to 4 decimal places. And why did they round to 4 decimal places? Well, if we go back, way back in the slides to where they were talking about what you're supposed to round to, which was actually quite a long time ago. We were back here. When you're using an original set of data values, round the confidence interval limits to 1 more decimal place than is used for the original set of data. Or alternately, if you're using the summary statistics, you use the same number of decimal places. Okay, so going back to the original data values that we started with here, these were all rounded to 1, 2, 3 decimal places. Okay, so we need to include 1 more decimal place than the original data values. So that's actually why we need to round these to 1 more than 3. So here's 3. We need to round to 4 decimal places. So that means we need to have 1, 2, 3, 4. So we don't need this one here. And then same thing over here. So 1, 2, 3, 4. However, because that next digit is 5 or higher, we have to round this 2 to a 3. So round it up. So that's going to become 9.0213. Okay? And then that should be pretty similar to the numbers they got. In fact, it should be basically the same. So let's see if we got, yeah. So we got exactly the same numbers they did here. So that's good. Okay, and then the only thing left to do is interpret the confidence interval. So we have talked about interpreting confidence intervals in great detail in the previous section. So I'm just going to kind of go to this next slide and we'll read through it, but it's basically just the same approach that we took for the interpretation that we used in the previous section. So they say we are 95% confident that the limits of 8.5901 grams and 9.0213 grams actually do contain the value of the population mean mu. So we did the same exact wording in the previous video. It's just instead of estimating P, now we're estimating mu. But we're still saying our level of confidence, which is 95% here. And then we're giving the limits. This was the number on the left side of the confidence interval. This was the number we got on the right side of the confidence interval. So that first part is basically identical to what we've said before. And then here's an interesting thing that they say that might be helpful in your homework. So they also say, if we were to collect many different random samples of 6 Reese's Peanut Butter Cup miniatures and find the mean weight of each sample, so they're talking about X bar for each sample, about 95% of the corresponding confidence intervals should contain the mean weight, or the average, the sample mean weight of all such peanut butter cups. I'm sorry, I said sample mean, I meant population mean mu. So actually they're talking about the population mean. So we're estimating the population mean mu using the sample mean X bar. Okay. But honestly, this first sentence is the main thing that we need to be using, because on your homework they're going to ask you to interpret the confidence interval. Look for this exact type of wording just with whatever numbers you have on the problem. Okay. All right, and then this is straight out of the book. This isn't as helpful, but I wanted to include it anyway because it's a little bit funny at the bottom. So in the book they say, we noted earlier that the sample is from a bag of 38 cups and the bag is labeled as containing a total weight of 340.2 grams. So the mean weight of a cup, Reese's Peanut Butter Cup, which are delicious by the way, in case I didn't make that clear already, should be 340.2 divided by 38 is 8.953 grams. Okay, so what they're trying to do here is they're trying to apply this to the real world. The confidence interval limits do contain the desired mean of 8.953 grams. So why does it contain the mean? Well, if we go back to the interval, 8.953 is actually between these two numbers. So that's what they're pointing out here. Okay, so what does that mean then? How do we use this? So the package appears to have been filled with candy in an acceptable way. It would have been better to obtain a simple random sample of 6 Reese's miniature peanut butter cups from six different bags from different regions of the country. I think what he means there is if he got it from different regions of the country and he did it randomly, then it would be more randomized, so be closer to a simple random sample, which is the goal. You want a simple random sample. But then the author of our book didn't have time for that. He needed to rotate his car tires. Wow. How lazy of the author of our textbook. Okay, well, anyway, that is hopefully helpful. I mean, honestly, the stuff that we're doing here is pretty similar to what we did in the previous video. So I'm hoping that most people are able to follow this pretty well. Okay, and then, like I said, in the real world, you generally don't know sigma unless you do a census. So some professors do like to cover the case when sigma is known. The problem with that is, I mean, if we do somehow know the value of sigma, in most cases that would mean we also would know the value of mu, because we would probably have to do a census of the entire population. But if we somehow knew sigma for the whole population, but we didn't know mu, then we could estimate the population mean using the standard normal distribution instead of the student t distribution. So we would do the exact same procedure, and you'll notice that this margin of error here looks very similar. It's just if you somehow knew sigma, then you would use z sub alpha over 2, which would be the critical value in the standard normal table, so table A2, and then instead of s, you would use sigma, because you know sigma. This is only used with known sigma. We're not going to do this in our class because it's such a rare case that it's not really useful in the real world, because, like I said, if you know sigma for the whole population, you've probably done a census, so you also probably know mu. So then why estimate mu if you know exactly what mu is? Okay, but there are situations where this is useful, so I just left this here, even though it doesn't show up on your quizzes, homework, and exam, because I wanted to give this like an honorable mention that you can do this if you somehow know sigma. But on MyLab and Mastering, I couldn't find any good problems, at least problems that I wanted to put in your homework, quizzes, or exam that cover this topic. So we're just giving this an honorable mention, but we're not going to have to use this formula. Okay? All right, and then just to kind of summarize what we've learned today, and then also an interesting case on the bottom of something that, just so that you know for the real world. Like I said, in most cases, in the real world, sigma will not be known because we can't do a census. And then we can determine whether we have a normally distributed population or not just by doing a scatter plot and seeing if the dots basically follow a straight diagonal line. Or sigma is not known and n is greater than 30. If n is greater than 30, then we can use the central limit theorem. Okay, so in the real world, this is the case that you're going to see in most situations. So that's the case that we do over and over again in our homework, quizzes, and exam. So that's going to be E equals T sub alpha over 2. So the student T distribution using table A3. And then times S over the square root of n. Okay, if you somehow did know sigma, but you didn't know mu, and your population was normally distributed, or you knew sigma and n is greater than 30, as they point out here in our book. In reality, sigma is rarely known. Then you would use z sub alpha over 2, critical value on the bottom right corner of table A2, times sigma over the square root of n, which is basically just this formula. It's just instead of t, they have z, and instead of s, they have sigma. But it's still the same formula. Okay, and then the case that we're not covering in our course, it's not part of the curriculum, but you might be curious about is, well, how do people do it? How do they do statistics if we know that the population is not normally distributed and we know that n is less than or equal to 30? So if that were true, we can't use either of these first two cases. So it turns out that the way people do that is, as you might have guessed, they use computers or advanced software, in maybe some calculators, but usually computers. They use what's called the bootstrapping method, section 7.4, or a non-parametric method. This is an elementary statistics course that I'm recording this video for, so we won't be doing any bootstrap methods or non-parametric methods because that's not a part of our curriculum. But I'm just mentioning this because confidence intervals are very useful in the real world. And like I said, in most cases, what we're doing is going to be the most useful process in the real world. So the student t distribution and then s over the square root of n, that gives us our margin of error. Okay, so that is it for these slides. And I hope you've been enjoying my videos. I will see you guys next time. Have a good day.